Good morning. I agonised a little for this and rather more for the second half as to what I should try and put in at the end of these lectures. And I think as a reasonable, the important comments I'm going to make relate to the next half, which of course I therefore will leave until I get to the next half, the final lecture 5b. But I think perhaps it's worth making one or two comments which bring together some of the various observations I've made in the work that has been going on, so far as I'm concerned, for quite a number of years. Most of the material that I've shown you up till now, including the standard background waterways material, a bit about solitary waves and the Gerstner solution, was to lay the foundations in terms of classical material, and then I followed that with some of the approaches and thinking that I've adopted to look at more detailed structures within the water wave problem using perturbation methods, having introduced you to the sort of language and ideas. More recently, when I say more recently, the last 20 years or so, as I've mentioned a couple of times before, I've been working with Adrian Constantin, and indeed since I retired many years ago, it's the only reason that I've been able to keep going. I really think without his impetus and contact, I guess I would have disappeared altogether from the scene. The sort of work that I've done with Adrian falls into two categories, one of two categories. I'm not absolutely sure whether I've made this clear, but it is sort of relevant to what I'm about to do. Until the more recent years, which is what I will develop more carefully in the next half, the work that I've been doing with Adrian either involves me doing some fluid mechanics, doing some asymptotics, whatever, and probably coming up with an interesting fluid structure, maybe a PDE that describes some system or other, and then Adrian will get involved in that. He would see whether he can prove the existence in general terms of such a solution. More likely, that tends to be pretty tough, more likely he would take the PDE and then explore that himself with some students, sometimes sending it off to other colleagues who do it numerically. So that's the one side. The other side, so in a sense, I suppose you might say that in that process, I'm the initiator. But equally, it could work the other way around, which is where this comes in. So Adrian, and working with other colleagues in the pure mathematics community, will look at some very general fluid flows and come up with some general results, rigorous statements about the nature of the flow. Sometimes, and it does apply here, such problems are then looked at numerically. So we have on the one hand some very rigorous results which tend to be rather general and give a general description. At the other end we have numerical results and not very much in between. And that's where I like to think I fit in. Try and fill in the gap in between rigorous but not much fine detail, and of course numerical results which are very detailed indeed, albeit in special cases. So what I want to do this morning, the first part, is to look at one of the problems in that second category. So I'm going to be looking at periodic waves with vorticity over finite depth, and I think I'd better put a couple of references up here, hadn't I? A sequence, I think it's of probably three important papers, Constantin and Strauss, between I think 202 and 202, and some of these are on the reading list, and if I mention the odd one or two that are not on the reading list, they're going to be in the papers that are on the reading list. So Adrian and Walter did some very detailed work on this particular problem, and I think I need to put another reference up, but I'll do that in a moment. And so they were able to prove the strong results that they were able to prove applied to constant vorticity, and that's the case I'm going to look at. They were able to make some statements, but rather weaker statements for general vorticity. Had to satisfy some very general requirements. Sorry. Some requirements had to be laid down for the vorticity, but it did not have to be constant vorticity. So they were able to show, for example, their solutions did exist which were symmetric, In some cases, they were even able to show, and then the numerical work confirmed this, that some waves can take extreme forms. In other words, they could be peaked, an angle at the crest, corresponding to the highest wave that I mentioned of the solitary type. They were able to show that, and this is one of the points I want to pick up in this brief presentation, that for negative vorticity, any stagnation point, there may not be a stagnation point, but if there is a stagnation point, then it's going to appear at the crest. In this scenario, there are no critical layers, so the extreme you'll reach is perhaps a stagnation point at the crest. For positive vorticity, if there is any stagnation point, then it's on the bottom. And because of the symmetry, it's going to be at the crest or directly below the crest. Okay. And they were also able to show that the horizontal velocity component below the surface is a strictly monotonic function. So those are relatively general results. There's no fine detail as to the structure of the solution. But then, I think I've given you this reference. 2008 did a very significant, very good numerical analysis, both of the constant vorticity case. Because it was numerical, as long as they made reasonable choices for the vorticity, they could run the code for unusual forms of vorticity, ones that we couldn't really, or they couldn't really handle analytically, and came up with some really quite surprising and amazing results, beautiful results. One other comment, it was this work which, and the results of this work that led me to the critical layer and the appearance of a critical layer work that I talked about earlier. Right, so the situation then, oh yes, that's the Coe and Strauss work. Now I'll pause and say, right, what can I hope to do? And it was really at this point that I got involved. I knew about this work, and I have to admit, Adrian's encouragement, he wanted to see whether it was possible to get some fine detail out using parameter asymptotics. And that's what I want to describe to you this morning. The particular case and the way in which the results appear, and the way in which non-uniformities appear in the asymptotic expansion, what it means and how we can handle it. So this really is a quite nice, compact, neat example of an expansion which may or may not break down because it depends upon the background scenario. But if it does break down, we can rescale and we can find out what's happening locally. The breakdown is associated with the appearance of the stagnation point, as you'll see. Right, so looking at this problem, and when I talk about vorticity, just think of constant vorticity. Don't think of variable vorticity for the various comments I'm now going to make. There are at least two different avenues that can be explored. You could introduce very large or maybe very small vorticity and something which controls the size of the wave. I have done both positive and negative vorticity, which is fixed, with a disturbance, an order epsilon wave. I've also looked at this set of equations, which I described to you, and they have to be transformed to get them into a form that corresponds to the work that was done in these earlier papers. The corresponding solution, if you did have very large or very large positive or negative vorticity, one can do really quite a lot of interesting asymptotics. That is a vast exercise. I'm going to pick out just one problem. Okay, so these are the familiar equations, but I've got to recast them a little bit, and I'll assume that we have non-dimensionalized, normalized already when we get to this stage. So, essentially, though, it is the classical inviscid model, incompressible fluid, no surface tension, and constant pressure at the surface. The classical water wave problem. So we have Euler's equation. The pressure, I think I've probably written it down here, measured relative to the hydrostatic pressure distribution. We've got the condition at the surface, which, having removed the hydrostatic pressure distribution, just becomes that, the kinematic condition. This is the free surface. We have a bottom condition in general, but we're going to make it a flat bottom. We have non-dimensionalized. Pressure is measured as the deviation from the hydrostatic, and I probably would have been worth just as a guide. This is going to be the periodic problem, so we're looking at a wave which is going to be described like that in this system. Right, so here it comes. We're going to consider one-dimensional periodic waves over constant vorticity. And one of the aims of this analysis, in fact, if you like, it was what Adrian wanted me to do, and it was a slightly different sort of exercise for me. That is, don't go back to the very beginning. Don't go back to the Euler equations and do the problem as I would. Don't do it that way. Do it via the Dubray-Jacotin transformation. I'll give you the result of that in a moment. And use those equations and construct the asymptotic solution. And see how the various properties of the solution are embedded in that equation. Right, well, let the speed of these steady waves be c. Go into the moving frame, and so introduce. I'm using the note that's slightly different from me. I probably would have used a psi there rather than a capital X, but I'm sticking to the notation that you will find in Adrian and Walter's papers. And u is then measured relative to that speed c. In which case, the equations that I gave you a few moments ago, reduced to one-dimensional periodic waves, will look like that. Everything there is what you would recognize. They're very familiar. So we've got the x momentum, the z momentum, continuity, the dynamic condition at the surface, the kinematic condition at the surface, and as I've already indicated, we're going to take the bottom to be flat, horizontal, so W is naught, and I'm labeling the bottom here. Again, it's just to be consistent with the earlier work, rather than translate what they did in terms of my terminology. I hope that's clear. Right, and they were very specific. We have mentioned it before. They use the Bernoulli condition at the surface. Okay. And we need the vorticity in the problem. So there is the vorticity in general, and I'm going to take the omega there to be constant. Okay, so the way to proceed is to introduce a stream function, naturally, in a problem of this type. So here's the stream function in terms of big X and Z derivatives. Right? And we need, for this particular formulation, the mass flux. You might remember when I talked about the appearance of critical layers, and it was driven by the observations, some of the observations made in this work, that we've got the total energy. That was on the previous slide, essentially the Bernoulli condition. We've got the mass flux, and we've got the vorticity. And if those are fixed, then you will or you will not have a critical layer. Right, so here is the mass flux. The symbol that Adrian and Walter used was minus p, so that's a constant, and then we can specify the value of psi on the free surface, which is 0 in this formulation. That's the free surface, and it's then this p naught. The minus there ensures that psi is then a positive number. P naught on z is equal to minus d naught. So that's mapping the problem into the stream function form, but that is hardly the end of the story. The neatest way to deal with this is to construct the quasi linear elliptic problem, which you get in terms of the function d. In other words, we're not working in xz coordinates, we work in x psi coordinates, and introduce the function capital D. I'm not going to go through the development. It's very carefully developed and explained, and all the various conditions laid down in these papers. The equation you get is that, where the omega there is that constant vorticity, a pretty messy looking object. Okay, and we have the condition at the surface, the Bernoulli condition, which is the one I've just described to you there. That's on psi is equal to naught. And in this formulation, d is naught at the bottom on psi is equal to p naught. Omega here is strictly a constant. So the starting point, therefore, for the analysis that Adrian and Walter developed is that equation. and it's going to be the starting point for what I want to show you this morning. We're obviously looking for a solution that sits between the top and the bottom. It's strictly periodic, so the big X, it's already been normalized, will sit between minus pi and pi. Okay. Oh yes, well that's obvious, and I've just said it, haven't I? Because of what I want to do in this problem, this is not a line which was followed by Adrian, but it puts it into a form which makes it a little more obvious what's going on, I think, from the perspective of singular perturbation theory, well, of asymptotics. If you carry out that simple scaling transformation, you get a form. This is the déroulées equation. You'll observe that under this simple transformation, the omega now sits out here and here and here. If you let omega go to infinity in here, this part, in other words, the left-hand side, the solution of that gives you the background state of the flow. I'm not going to take omega going to infinity, but it's a nice interpretation. Correspondingly, of course, this simplifies as you let omega, mod omega, go to infinity. Right, so we're getting down to the stage where we can begin to analyze a particular problem. So this is what I mentioned a few minutes ago. One obvious, and it's going to be the route I will take, but only for positive vorticity, will be just to keep omega in this system as a fixed parameter and then impose a wave perturbation, and that the amplitude of that wave perturbation will be our small parameter in the system. Conversely, we could take that system of equations and ask what are the properties of the solution in the expansion sense if you allow omega to go, well, mod omega to go to infinity. I'm only going to do one of those four options. Okay, here it is. So I'm going to examine the small amplitude, so that's going to correspond to linear waves with fixed positive vorticity. We start by writing down, and you can see it because of what I wrote down on the previous screen. You can extract it very quickly. We need to perturb what corresponds to the uniform, what is the uniform state that corresponds to the constant vorticity. And written in these variables, it takes this form, where B is a constant, P naught is the constant we've already introduced. The Bernoulli condition then gives us the relationship between B, P naught, omega, that's just a fixed constant here, a fixed parameter in this system, determining Q. Clearly, we can only get a solution if B is greater than or equal to 2P naught. I'll come back to that particular condition shortly. Okay, that's the background state. Or the way to interpret this is to say, I guess, you're going to be given Q, you're going to be given P naught, you're going to be given omega, so you have to think of that as an equation for the B, which then goes up here to give you the background state. What we now want to do is, taking that as the starting point, perturb it. This would be more naturally done, as I said in my introductory comments, if we were working from the Euler equation. But because it was important to see what happened within the déroulées structure, I stuck to that equation. So I'm going to do some asymptotics on that equation. And that means using this as the start solution, perturb it by a parameter which measures the amplitude of the wave. So I'm looking at this very simple case. The wave on the surface is of amplitude epsilon measured relative to, if you like, an order 1 depth. Okay, everybody comfortable? We've reached the point now where virtually I could have said, here are some equations, let's do an expansion and see what happens. I hope I've given you just a little bit of background so you know what's going on here. Right, so it is routine. It's really what you conclude, having done the routine things, that gets interesting. So, if you put in, and obviously it's a very messy non-linear equation in D, perturb that D naught background state solution, and obtain the equation for D1. Here it is. Doesn't look good, but you would expect it to have some simple solutions, because if we go right back to the Euler equation, we have a relatively simple background state. We'd expect to be able to get harmonic waves or something like that as the solution. So it shouldn't be too bad. Okay. This is what the various conditions, so that's what the Bernoulli condition becomes. Because we've got D0 is 0, it just becomes D1 is 0 on the bottom. Again, this is not as bad as it looks once you have made a choice for the appropriate solution of that equation. I'm going to go back just for a second. Right, that equation does have, as you would have expected, a solution that corresponds to a solitary wave, for example. If you just write down that equation and don't impose periodicity conditions, then that does have a solution that would recover the Sheck squared function. It's hidden in there as being a small amplitude wave sitting on the surface of the water with a background vorticity. However, we don't want that solution. We want a solution which has got the appropriate oscillatory structure. There it is, cos x. It also satisfies the bottom boundary condition. And if you're familiar with these sort of calculations, then you'd expect to see something like exponential, or if it's a finite bottom, a Shine function appearing. This thing is what replace, in the very simple theory, a z, if you like. Now, that is an exact solution of that equation. It is the appropriate choice of solution which ensures that we have something which is periodic minus pi, and it satisfies the bottom boundary condition. That isn't quite the end of the story, of course, because we now have to satisfy the top boundary condition. This plays the role of a dispersion relation, if you think of it like that. Also, you'll observe that we can get real solutions only if omega upon p naught is less than or equal to a critical value, and you can easily compute, but you have to compute. You can't do it analytically. It turns out to be about whatever that is, 7.009. That description then with the background state, that's the D0 function, and this D1 function with the constraint for the existence of this solution describes the leading order and the order epsilon problem, albeit in Euler terms relatively simple, but of the Dubray-Jacquetat version of the problem. So that, if I summarize those two bits of information, that is what the solution looks like. I'm going to pause there and have a drink and just check if anybody wishes to make any observation. I'd like to think that if you can accept the formulation of the problem, which is in these papers, what I'm describing, and that's the beauty and the strength of this sort of approach. It is straightforward, it's apparently fairly simple-minded, but you get a lot of fine detail out, and that's really the emphasis I'm trying to put on it. Okay, I actually can't remember what I've written. Oh yeah, okay, that just clarifies. So that is just defining what all the various parameters are that are in this particular system, describing the linear perturbation of the background state using the DJ equation as the starting point. Okay, right, I'm going to go back. Don't quite want to uncover that. Now I want you to have a look at this expression. What you've got here is an order 1 term. Here is the wave perturbation term. And what you need, and there's the small parameter. So as I've shown you, I'm going to say as we learned. I hope I can say as we learned, but as I showed you. What you need to ask yourself is that solution, in our terminology, uniformly valid on the domain where this solution is to exist? And we certainly have existence theorems. We know there are periodic symmetric solutions, etc., etc. We've got that. That's the beauty of doing this sort of calculation here. We do have those theorems in the background, so we know that this has got to be a proper approximation in the asymptotic parameter sense of the problem. Right, well, if B is not close to 2p naught, psi goes from naught to p naught, if you remember. That's the domain of psi here. That expansion is uniformly valid. Okay? Providing that is not small, then this remains an order 1 term, this remains an order epsilon term, and indeed it's quite easy to check that the higher order terms involve proportionality to a term like that, epsilon over square root raise to the power 1, 2 as you go down the asymptotic expansion. So if this one fails, all the others fail, but they fail at the same order, in the same way, whereas if this doesn't fail, none of them fail. There are no other non-uniformities there. So it's the beginning of a very well-behaved asymptotic expansion in epsilon. Right, so we could just stop the talk at this point and just say, well, that's it, okay, dead easy, bit tiresome in the sense of doing the calculation, and it's a clumsy way of doing this particular problem using DJ rather than Euler, but we're finished. Of course we're not. Only a mad person would think I'm going to finish there. So you've got to listen to me for a few more minutes as I waffle on. Okay, so if there is to be a stagnation point, I'll backtrack just for a second, and that solution does not predict a stagnation point as the wave propagates. This does not generate a stagnation point here or here. Because of the way I formulated this, I think I listed it, didn't I? This problem, because I'm doing omega positive, will have or could have a stagnation point at the bottom. The corresponding problem, by the way, for the top is much more complicated. It really is a much messier calculation. If you try and do the sort of thing I'm doing here, but ask what's happening near the peak, rather than at the crest, rather than at the point directly below the crest. So we're now going to take out of this problem a special version of this problem. Let us now suppose that our parameters, which are determined from these various results on the board, let us suppose then that b minus 2p naught is order epsilon squared. Well, let's see, why did I choose that? Well, if you come over here, you will then see, remember that this is the same quantity, and that psi approaches p naught as you approach the bottom. Okay, so these terms are essentially, if psi is of the same, is close to p naught, then these two terms are the same size. We're not talking about them cancelling out; they're just getting in the neighbourhood of the bottom. Those two terms are the same size. If we choose that, make that choice, then the breakdown of this expansion will occur where psi minus p naught is order epsilon squared. Now, why is that? Well, as you approach, put b is 2p naught to within order epsilon squared, that likewise, this of course remains order 1. Remember, that's a shine of this thing, which is epsilon squared, so epsilon, that goes. But over here, you have root epsilon squared, that's epsilon, which is the same size as that term there. In other words, there is a breakdown of this expansion near the bottom if you have this particular choice. So this asymptotic expansion in those circumstances breaks down. Other circumstances, no stagnation point, it does not break down. Now, it's this sort of fine detail that you're not going to get in the theorems. Okay? Exactly how it happens and the way in which you need a breakdown and the precise scalings in terms of epsilon telling you what's going on. Right, are everybody happy with that? So now I look at a new problem. The new problem is specify the parameters b and p naught such that they are indeed order epsilon squared. That now becomes the driver for this special problem, and off we go. So here we are. Let me introduce a new parameter which replaces b minus 2p naught. So I've just called that, I choose a positive lambda and write it as epsilon squared lambda squared. And then, having made that choice, and that's just a choice of parameters in the problem, which I can always do, having made that choice, we now know, we've just seen it, there's a breakdown of this asymptotic expansion when psi minus p naught becomes order epsilon squared. So let's introduce a new scaled variable valid in the neighbourhood of the breakdown region. So here it is. So I'm going to define psi, the original psi, to be p naught, to make sure that I'm sitting between naught and p naught. I define it as minus epsilon squared capital psi, and capital psi is greater than or equal to 0. We've already seen it, but let me just remind you, when you put this information into here, the breakdown, I think this relates back to a question I had a bit earlier in the week. the leading order problem now is not order 1. The leading order problem now has become order epsilon. This remains epsilon, and what we've shown is that that term reduces and becomes the same size, and that heralds the breakdown of the asymptotic expansion. So in other words, D in this region has become order epsilon. So that means we have to redefine D. So here we are. So I've redefined D. D is now epsilon times some new function, function of these new variables. Well, one new variable anyway, working in terms of capital psi rather than little psi. And this is typically how you do these problems. You do an expansion. If all is well, end of story. If it's not, having obtained a breakdown, rescale and go right back to the beginning. I'm sorry, there's no other way of doing it. You just got to go right back, solve that problem, and you know what we then have to do, almost always, is match. We've got an exterior region and an interior region. And we've only got, the leading order has got the boundary conditions on, but we've got no other information. If we're working at the bottom here, we can't use the top boundary condition, but we do have a solution that's valid away from the bottom, so we aim to match those two. Okay, so that's what the new equation becomes. And actually, it's pretty straightforward. The beauty of this system is that, look at that, you just get all the nonlinearity over here. There's some there, you'll notice, but you also got all of these, and all of these are the same order when you carry out this transformation, this scaling of the variables. They're all order epsilon squared. The bottom boundary condition, because of the definition I used, now just means that capital psi is 0. Sorry, d bar is 0 on psi is equal to 0. And, well, I've just said it, haven't I? And as you move this is a scaled region which is very narrow. As you move away from that region, which corresponds to capital psi getting very much larger, so formally it's capital psi going to infinity, and little psi tending to 0, okay? It's like that. Well, little psi tending to p naught in this case. That's going to be the matching condition. Okay. Oh, I see. I did click it inadvertently, but well, you've seen it already then. Right, one can relatively readily solve that differential equation. Remember, it is just that. I'm just looking at the leading order, and the correction here is rather nice. It's order epsilon squared. You can also see that if we then were interested in large omega, then that's even smaller. However, that's by the by. That's not the route that we're going to follow here. There is a solution of that equal to 0, which takes the... I see I've jumped a gun a little bit here. Right, it actually takes the form 2 psi plus an arbitrary function of x minus this... that's squared. So 2 psi plus square root of arbitrary function of x squared minus an arbitrary function. Matching then gives that particular choice. So the matching condition determines what this function is in order to match to the solution that we had on a couple of screens back. It has to take this very particular form, and that completely determines the solution in this scaled region. This is the leading order, so I've put a behaves like here. This is the leading order as epsilon tends to 0 of this system. It is easily checked, and you look at the nature of that solution and think of what the derivatives are going to be. And you can check that this thing, because of the have I said that right? Yeah, well, I have checked it, but I'm not sure whether what I've just said is right. There are no non-uniformities of this expansion as you go downwards. The corresponding approximation that we've just used in the parameters now becomes that, because remember we've made this choice that b is close to 2p naught. So this in turn has an asymptotic approximation associated with it. Okay, now I need to write something on the board, because I realized last night when I was looking at this, and I forgot that I hadn't put in an a of x, which I should have done. I think probably when I was writing these things 2 or 3 months ago, I was very concerned about timing. I don't think I need to have been, but I didn't know at the time. So I could just make 2 observations. First of all, the form of this, the solution, takes this form. There's an arbitrary function, so let me actually spell it out, minus a of x. That's the form that the general solution takes when you solve that equation, seeking a solution of the form that can match. There are other solutions, but you need the one which one is consistent with the equation and with a suitable matching condition. So you get that, and then there's the A of x, and I think I've probably written it, yes. And big U, that's in the moving frame. The behavior of that function, based on our asymptotics, I'll write this with a bit of care so you can see it, turns out to be minus epsilon. It's an order epsilon term via the transformations that we've just been using. It turns out to be this. It's essentially what I've just written down there, but I think it's worth making clear what the form, what the form of U is. So now I can go back to the statement I've actually put on the screen. One of the issues is, and it was really the driving issue here, was to get the fine detail of the structure out, go for the stagnation point, and then just see exactly how, in some detail, how the stagnation point arises, what we can say about the parameters. Well, the stagnation point is going to correspond to, let's move over here, to psi is equal to 0. Sorry, the bottom corresponds to psi is equal to 0, so you can see where we're going. It's very simple now. Corresponds to psi is equal to 0. If this term is non-zero, remember it's symmetric, even at the bottoms, that's where, and under the peak, where x is equal to 0, then that need not be 0. But we can now be quite precise. It will be 0 if the parameter lambda is equal to 1 over square root omega. If you make that choice of parameter, then there will exist a stagnation point on the bottom. Right, so, oh, I've got a picture. Excellent. Right, so, using it's not very exciting, but it's nice to see that you get the right structure here. Now, that doesn't look very much because the region is very narrow, and I've made the region about 0.1 or something, maybe 0.15, something like that. So what I've done here is very quickly sketch, and I'm afraid when I did it, and I haven't bothered to improve it, I used a rather crude printer, plotting and printed, so it's not as good as it could be, but I'm sure you can squeeze your eyes up and visualize the beauty of those curves. Essentially, what I've done is to merely plot the solution in terms of the asymptotic expansion. So I've got an outer region and an inner region, and I've merged the two together so that I get a nice smooth transition numerically, just using the asymptotic expansion. Now, the only thing to observe here, this is essentially from about here, the outer solution. Here is the inner solution, and I've added rather more lines there, and only if you look at it carefully, because it's really narrow, you'll see that the amplitude, as it must do, is coming down. Compare that curvature with this curvature. But that's all there is to it. All I've done is simply just produce what the curves look like. One of the reasons being that exactly those sort of pictures were, of course, produced by Coe and Strauss in their numerical work. I think I've also got... Yes, this is the perturbation velocity profile below the surface. So this is the big U function, essentially. So what we've got here is, there's the surface. Here is the bottom in this particular choice of values, numerical values that I ran for the computation. And here is the stagnation point. So, again, there was nothing like that in, and there could not be, anything like this in Constantin and Strauss, but of course there's a lot of pictures like this in the numerical work. Okay, so timing, as I thought, would be reasonable. What I've tried to show then is that in the context of what I've been doing in my relations with Adrian, is to try and put in a little bit more detail using formal parameter expansions to try and extract some analytical detail. So, as we've seen, at least if you fix omega and look at epsilon tending to 0, the asymptotic structure is fairly simple, but it does have, in a slightly unusual way, it is a rather unusual type of non-uniformity because you have to make two choices. In other words, you have both to get the parameter right, and then you ask, is it valid? If you choose different values of the parameters, there is no breakdown in this asymptotic expansion. When it does break down, as you've seen, it's the routine procedures that I've tried to encourage you to think about: break down, rescale, start the problem again. We found the solution valid in the neighbourhood of the bottom, and in particular, we've got some algebraic structure to the nature of how the stagnation point appears and the behaviour of the solution in the neighbourhood of the stagnation point. And of course, as you would expect, all of this agrees with the general results that have been obtained and with the numerical results, naturally. I have already commented that the change of sign, so take the vorticity constant but negative, can be done but is much more complicated than this. The structure, getting the solution and the structure of the equations at higher order is nowhere near as straightforward. But an interesting issue which was done by Cohen Strauss was to ask what happens as you increase the vorticity, the strength of the vorticity. And finally, this technique can be used, providing you can find an underlying solution for some appropriate variable vorticity, to quite readily look at the structure in the same way that I've done here for problems which certainly cannot be handled in, with any reliability analytically, even though, of course, it can be handled numerically. So that brings us to the end of the first part of this morning. I hope that what I've tried to do here is, again, rather in outline, is to show you how, given a flow, given some hard, rigorous results, and in this case numerical results as well, we can extract some fine detail. I would say to you, don't worry too much about the actual results. I hope they're marginally interesting. Just look at the technique, what it is possible, that what can be done using parameter expansions. Okay, right, far away with your questions. Right, welcome. Now for something which is verging on being completely different. I said in my preamble before the previous section that I had some difficulty choosing what to present at the very end. You will know from the comments that I've made that the work that I've been doing with Adrian has changed somewhat. 6, 7 years ago, something like that, the move was away from waves, nonlinear waves, slightly more general fluid mechanics, towards flows in the ocean and the atmosphere, something which I think I commented on it earlier in the week. I was initially reluctant to go down that road, but that's the road we've gone down. One of the effects of this is the dynamic has somewhat changed. So whereas, as I was describing earlier this morning, Adrian might do something and pass it to me, and I might do something and pass it to him. Really, for the last few years, we've been working in parallel on these problems, once Adrian had persuaded me that it was worth doing. I wanted, therefore, to end on an area which is now of much more interest to me. It's the one I'm looking at and have been looking at for these last few years. And I have to admit that what I would have preferred to do, if it had a different title to this, this whole week, would have been probably looking at some large-scale motions of the oceans or the atmosphere, which would not necessarily involve waves at all, although we have, of course, done some work on waves. So not only was it slightly outside the remit of this week, it would also have required me to do, I suspect, a vast amount of background description and chatter to put it all in context. So, in a sense, that's a little bit of an apology for what I'm about to do. What I've opted to do is something which is as close as I can reasonably make it to what we've been talking about this week, but is then touching on some of the newer material that I've been working on with Adrian. This particular problem, I'm going to have to give you the background to it, which I hope you'll find interesting, was one of the very earliest calculations that I did in this arena. And the reason I did it, and the result of doing it, I think is an interesting story, which will unfold as I chatter to you now. So, I'm going to look at a very, very specific type of flow. It's called the EUC, the equatorial undercurrent in the Pacific. And I will, of course, naturally, as I've just indicated, talk about waves. Okay, so now I'll pause for a minute or two. I don't know whether this sort of picture has any meaning to you, but let's have a go. This is the Pacific equator. The basic structure we're going to be looking at, a more careful picture coming up locally in a moment or two, is the equatorial undercurrent, which is cold water moving here up and back on the surface. This, by the way, the structure of this varies somewhat as climate change has had an effect, and indeed the particular structure that this takes and the corresponding Walker cell above it is the thing that's mainly affected by El Nino and El Niña. Indeed, as we go through the cycles of Niña and Niño, this can either strengthen or indeed break down into two cells. So more or less in the middle. So you've got one cell there and then another cell there. In this diagram, you will also see other phenomena. Again, I don't know how much, some of you will know this very well, others perhaps not so. If this is the equator, so there's the equator, there are two enormous circulatory cells that go in a torus around, one above and one below the equator. That's known as the Hadley cell. I think roughly from 0 to 30 degrees. 30 degrees to 60 degrees, roughly, in our current climate. There's another big cell called the Ferrel cell. So Hadley, Ferrel, and then there's the one which is a torus that more or less sits with a little hole in it at the poles, the polar cell. Now, that's what we've got at the moment in the climate. Because of the climate structure, there are certainly suggestions that that three-cell structure might well vary over the next few hundred years, and we know that it must have been different a few millennia ago, when probably there was a single cell that went from the equator to the pole. Now, that's the general scenario, and I'm going to be looking very specifically at what happens in the vertical plane at the equator with this structure. We've got cold water, we've got a thermocline because we've got warm and cold here, we've got flow back, flow in this direction, etc. Really quite a complicated structure. Consequently, the sort of things I'm going to talk about in part in this last talk will be a little bit of more, I suppose I might call it conventional applied mathematics that sometimes I have to do, together with, of course, waves and perturbation theory. Okay, so I'm just going to mention a few things which could be, should be included if we were going to do analyze it in the grand scheme of things. So we've obviously got all of these elements, wind-driven surface waves. We've got underwater currents, that's what I've just been showing you. We've got upwelling and downwelling. We've got thermal density and salinity stratification. I'm sure you can think of other things as well. But more significantly, perhaps in the current, literally general word climate, is that these will all change, and do change on both long and short time scales, and clearly they are affected by the climate and indeed affect the climate and the knock-on effects to climate change. This is where things get, from my point of view as an applied mathematician, different as compared with much of the work that is normally done in oceanography or atmospheric sciences. And it's the reason why I got involved in this, and Adrian thought that it was, between the pair of us, worth looking at. Almost all of the work that is done is based on what I would call, I hope I'm not upsetting anybody, ad hoc models. That is, there's a very good grasp by, in terms of physics, generally speaking, of what is going on. It ought to be this effect, and it ought to be that effect, and it ought to be that effect. Oh, let's write them down as an equation. And they're going to be terms, roughly speaking, that come from equations of fluid mechanics. Okay, it may be compressible, may be incompressible, certainly it's going to be viscous. Just throw the terms together. Now, I think it's fairly evident from the way in which I've been talking, particularly earlier this week, that that is not the way I operate. Absolutely not. My philosophy has always been that you start with an accepted set of full governing equations. That might be Euler, it might be Navier-Stokes. You may have to be a bit careful about the role of viscosity, what sort of viscosity you use in Navier-Stokes perhaps. But you start with what is generally accepted as the correct equations. general governing equations, suitable boundary conditions and initial conditions. Then you do what I've tried to show you. You carry out a non-dimensionalization, introduce your parameters, which are relevant, and they will change a little bit from one problem to another. You non-dimensionalize, introduce your parameters, and then just see if you can do a parameter, parameter expansions of that problem to guide you towards what is thought to be an interesting phenomenon. The net effect of this is, which is why I'm going to have to be a little bit careful this morning. It happened a couple of times earlier in the week when I got a bit overexcited and I just kept on talking. When we started doing this work, obviously in a sphere, in a rotating frame, it soon became evident that we could do, Adrian and myself could do far more work than appears ever to have been done. There's virtually no attempt to include spherical coordinates, for example. It's all local tangent plane. And I certainly couldn't understand that, even when they came to us and said, well, we don't really understand spherical coordinates. They're a bit complicated, aren't they? What? So that, and we get a lot more fine detail and a much more general validity when we use these approaches. Hidden, embedded, quite often, but not always, are some of the standard results. So I'm trying to give you the philosophy that's driven us for the last few years. However, much as I would like to talk about all of that aspect, I pick up this problem, which was almost the first problem that, well, I guess I looked at it, and Adrian guided me a little bit because I knew none of the background that I've just given you, to do a calculation which, in one sense, is absolutely routine, and I think the word I would use is trite, but it had never been done before, and that is the thing that really surprised me. Okay, so let me say a little bit more about the EUC. So this is going to be, this is data to give you some idea of what is going on and therefore how we might attempt to carry out a modelling of this. Right, so we've got, essentially, we've got warm water, we've got cold water, there's some, obviously, variation in temperature, and roughly speaking, here, roughly speaking, we've got ourselves a thermocline. So what we're going to be looking at is a model for the position of the thermocline, that is relative to density, and will only be a density change that I'm going to incorporate above and below, with flow in the directions that I indicated on the previous effect. I think I've got them coming up here. Here we are. Oh, I think you'll find that that's land masses. You know, there's okay. There's something sitting there. If I remember correctly, we're at 60 degrees west here, and yeah. Right, where are we? So, I mean, I'm going to be looking at this bit, you see. I should be in there. Right, if you look at this diagram that I've just produced for you here, this is getting closer to the modelling that we're going to carry out. So we're looking in this region here. We've got the EUC, the undercurrent flows, as you'll see, from west to east, but the surface flow goes from east to west. Here, in this sketch, roughly speaking, is the thermocline. And it's the variation of that in the amount of cold water that's pumped up that is an element within the El Nino effects. That is therefore a schematic of the type of model that we're going to take. And in this business, you do have to, at least with flows like this, you're going to have to start with some sort of appropriate model. It's getting the useful structure, maybe wave propagation in this system, which is where we're going, of course, with a model that reasonably represents what is going, hopefully captures all the main elements of the existence of a thermocline and a rather complicated velocity field, which will be the underlying flow state on which you would put a wave, you would perturb. Okay, so it's pretty obvious from that diagram there. We're going to consider flow in the vertical plane, essentially at the Pacific equator. We're going to be in rotating spherical coordinates, but as I've written there, approximated locally. This was one of the very earliest calculations that we did, and indeed, local is all you really need here. I'm not talking about large-scale motions in the atmosphere, Hadley or Ferrel cells, or large gyres in the ocean, which could easily be 1,000 kilometers across, and you really do need to make sure that you've got the appropriate and accurate spherical coordinate system, not approximated locally. Right, so these are the sort of equations that you've seen before, but with some small adjustments. So we've got some sort of background flow. Essentially, we are going to perturb a background state and ask, what do we get? So this is the background state. So we're going to have some sort of velocity profile. Epsilon measures the size of the disturbance, as we've had before. Following on the discussion over the meal last night, as some of you will remember, our epsilons do tend to 0. Even if we are told some weird people use the symbol epsilon and let it get a little big. I couldn't believe it either. There's also a contribution from Coriolis in here, these two terms. Otherwise, it's what you'd expect to see. So it's an adjustment of what you've seen before. But we've also got a thermocline in here. So these equations apply. I'll give you the boundary conditions in a moment. These equations apply, or shall I point to these two, both above and below the thermocline. But when you have the thermocline in place, or either above or below, you have to adjust, in this model, the density. So in this normalized system, the density is 1 if you're above, and it's cold, a little more dense underneath, is 1 plus r. And to give you an idea, r is typically about 0.005 in the Pacific. Right, we've then got the appropriate boundary conditions. So at the surface, which again I'm measuring as z is epsilon eta in this case, so z is 0 will be the undisturbed free surface. We've got a pressure condition, and remember we do have some sort of background state that's got to be maintained with that u of z, and a kinematic condition. Right, what have I got here? We need a kinematic condition at the thermocline, and we need a pressure condition across the thermocline. This has to be worked out from the general physical principles that underlie it. I'm not going to go through that, but we can work out what it is. It has to be known. You have to be given the conditions that you wish to impose above and below. Right, but that does depend upon the shape of the thermocline, and as you see, there it is. Even though we have oscillations on the thermocline and on the free surface, which are significantly different in amplitude, when we're going to measure them all, and it's natural to measure them all via a single parameter. So we could still allow the ratio of capital H to eta to be maybe 20, but we are still saying that that structure multiplied by epsilon is an asymptotic approximation, so it tends to 0, as epsilon tends to 0, but we can have the ratio of those quite large, and that is what we find, and some of you may already be aware of that. Okay, so this is the continuity at the thermocline, pressure continuity. I think I've said everything that we need. So, superficially, quite a complicated system, but fortunately we do have a mechanism for getting a handle to some extent on what is going on. Namely, but given a background state, perturb it, see how far we can get. Okay, oh, and the bottom condition just come up. Yes, though we were talking, I think it was at breakfast this morning, about the screens that one uses, and the fact that one really needs to make sure there isn't too much information available. Use the screen as the prompt to talk, and whether you've noticed, I know when I've got to the end. Usually it's at the bottom, but not always. I always make sure the number comes up. And if you watch, the number's gone, and it's come back. If I'm really on the ball, I put the number up there to say I'm on 5, but what matters is whether that one appears down there. I hope you're learning quite a lot of useful things, you know, if ever you have to go through these. This is the last time I'm going to talk to you, so I can chatter a little bit, can't I? I learned very early on, never use a back screen which is white. Because if you do, you're forced to put the lights out. It's very difficult to see a white screen with lights around. Whereas if you take a slightly darker screen, and I like to think this is a pleasant blue, and then yellow and white, sometimes a little bit of pink or a little bit of light green on that. It's legible. I mean, it's clear, isn't it? Very clear. And you can have all the lights on. You'll still be able to see it easily enough. Right. Okay, so don't know where we're going now. Right. I've talked in general terms about what this parameter is. It's measuring the amplitude, but I'm going to be precise. We're going to measure it relative to the average undisturbed depth of the thermocline, which is in the Pacific at about 120 meters. We have a background state here. and it is purely horizontal, it just goes in the x direction, and it has to satisfy that system of equations, yes, that equation, with rho and above and below. Rho is 1 above and 1 plus r below. And we're going to model this. Let's be quite clear about it. This is, in one sense, very crude sort of applied mathematics. We have to be given something to get us started. We're going to say, look, this is the state of the ocean. Let's put a wave on it and see what happens. But we've got to be given the state of the ocean to get started. So we're going to be given U of Z. We're going to choose a model for U of Z, one that we can manage, of course. Is there anything else that I've said? The parameter omega, that's the is a contribution for the rotation. This is the rate of rotation of the Earth sitting in here. Right, and those are all the other parameters, and I think maybe it is only omega actually, are treated as independent of the limiting process. So they are fixed. It doesn't matter what number, what value they are, the size, they are fixed. And they can be as large or small as you like, but they do not vary as epsilon varies. That's the crucial point. Here we are then. We're now going to choose a background flow to represent the EUC. So the plan now is routine. And I have to tell you, it is tedious. And it's because of the way I tackle this problem, it's very lengthy. So yet again, I'm going to say, I'm not going to give you the details. I'll tell you why I did it the way I did it. And rather surprisingly, the reaction we got when the paper was published. Right, so the plan hereafter is to take this background state that I've started to describe, but we will choose that function, very simply, to model what is observed in the Pacific. Expand for small epsilon, use our normal Taylor expansions. In this case, it's about z is equal to 0, because that's where my surface is. So I'll then talk a little. I'm not going to give you the dispersion relation because it is, I mean, I don't know how many screens I'd need for it. It's immense, but it's absolutely explicit. And then I will make some comments about nonlinearity. So the theme will be, the driving theme will be waves, as it should be, and I'll say a little bit about nonlinearity, particularly how it relates to some of the things I said earlier this week. Okay, so the first issue is to make a choice, a very simple choice, that models the EUC. And that is the choice that I made. It's absolutely the obvious one. So it is piecewise linear. So we've got piecewise constant vorticity. This is the backflow. Okay, this is the flow to the west. Here is the EUC. It's got 0 here and then below. I'll put the thermocline and other things in a moment. And there's the description. What it turned out was very nice. This is the natural way to do the problem if you're going to take the simplest choice possible to enable you to proceed, is to have variable positions here. You've got an L, an M, an N, and all these various, well, V and W. The V is that way, W is this way, speeds. And that's just carried through the analysis. And it did turn out that because we did that, it proved to be very successful. I'll tell you why in a moment. Okay, if you're interested, just for the record, for the EUC and using this approximation to the profile, then we have estimates for the values of these various parameters. One of the things we learned when we got reaction to this rather straightforward piece of work was that there are at least two or three other places around the, yes. I'm coming there, I promise you. It is not in that picture. This is in isolation. This is just saying the velocity profile, yes. It'll come up on the next screen. And it's important that we know where to put it and how it fits in there. I'll come to that in just a moment. What was I saying? Yes, there would seem to be 2 or 3 other places around the world in the oceans where perhaps not as on a grander scale as the EUC, but there are similar structures to this, where you've got a reasonable variation of velocity from top to bottom and at different levels. And that is what it appeared excited some oceanographers, because all they've got to do is to change the numbers in here and fit it to some other flows. what is amazing, I'm almost letting the cat out of the bag now, is it had never, ever been done. I mean, it's tiresome. It's the sort of applied mathematics that I prefer not to do. I'll be honest, it's not what I want to do. But if you're going to tackle these sort of problems, you have to be prepared to do them sometimes. But it just never had been done. I'm still surprising. Okay. So we have the linearized problem now. So we've got a background state. We have a linearized problem, and the background state now appears in here. I think that's it. That's what I need to say. Bearing in mind, again, this row, you're either above the thermocline or you're below the thermocline. We're looking for an irrotational perturbation to make it nice and straightforward and simplistic. The Taylor expansions imposed upon the boundary conditions give us this system. Obviously, I should have said it at the beginning, although it's quite obvious, isn't it? This is absolutely steady. We haven't got here, we don't have to worry about any initial values, initial data driving this solution. We are hoping, expecting that we're going to get a reasonable solution and it exists for all time in this scenario. Okay, there's the bottom condition, and here's the pressure continuity condition that goes above and below the thermocline. Right, picture coming up, so it must be the next one. Okay, here we are. Now, to solve this problem is absolutely routine but very tedious. You actually have to solve the problem in 5 different regions, looking for a harmonic wave, for example. Here's the thermocline. Right, so this sketch here is the background profile, and we know from the data that the thermocline, even though it may have quite a large amplitude, maybe 10, 20 meters, definitely always sits in this region here. And that, so far as doing some getting the dispersion relation, is the fundamental assumption that I make, that it always remains in that region. It does not move outside and enter either this region or this region. It does remain, and that is a pretty broad region in practice. And I say all the data suggests that it even though it's got 20-meter amplitude sometimes, something like that, it always remains in that region. But that is the basis for our model. So in other words, as I've set it up, it is, yes, I've got this, I've taken a sort of center line. Now, in this normalized system of -1, yes, because I use the average depth of the thermocline to fix the non-dimensionalization. So this is -1, and it's plus L and minus M relative to that. They needn't be equal, but they can be specified. But importantly, the thermocline will always sit in that region. So what we're going to do, I'm not sure what I've written on here. Hang on a second, see what just comes up. Yes, okay, well, that's really what I wanted to say. It's just a matter of now seeking a solution. It's a linear system. It's got very simple coefficients that are either constant or linear in Z. We can seek a solution of that system, which is essentially harmonic in, to see a harmonic wave solution with an arbitrary wave number. And then, of course, you have to solve either from the top to the bottom or the bottom to the top. You've got to solve for each one of these regions. And here, this is above and below the thermocline. Okay, so you've got there, above and below, and there. It is a very lengthy calculation. And what I think surprised me is that this had never been done. To me, it seemed to be the starting point if you're going to do any sort of analysis like this. So you just get on and do it. All that appears to have been done is that some work making assumptions about the wave number, k tending to 0, k tending to infinity, something like that, and looking at the behavior of the flow in localized neighborhoods without putting in the complete profile. Okay, well, straightforward. You just get on with it. All right. Well, I've already said it already. I'm not going to reproduce it for you here. We've got it, and from the feedback we've got, it's clearly been very useful because nobody had produced a dispersion relation which was valid for all wave numbers and allowed there some variation in the choice of model, at least in terms of varying the constants. Okay, let me just spell out for you some of the observations that we're able to make. We can deduce from that dispersion relation. So, as I've said, it's valid for arbitrary k. We're normally interested in long waves. So let me extract from that a little bit of information for you, just to show you that we can use it directly. I won't dwell on this. It's not going to be of any great mathematical interest at all, but you might be intrigued to see how good the results are. So first of all, I'm going to look at what I will call intermediate long waves. So that means there is a d in the dispersion relation. So I'm going to let k tend to 0, but kd tend to infinity. So that means that they are long relative to the scale I'm measuring, which is the average depth of the thermocline, okay? But short relative to the ocean depth, okay? And by the way, if you remember the figures I gave you, if you take the down to the thermocline to be 1, typical average depth on that scale is 33. Okay, right. So if you take the dispersion relation, play around with it, we can get some explicit expressions for the wave speeds. There are 3 of them. There's a plus or minus there, and there's one there. And the typical values, that is, putting in those values that I mentioned earlier for V and W and R, etc., give you these speeds. So you've got 2.7 meters per second, etc. eastwards. There's a westwards, that's 1.7 and 0.55. And here, I'm giving you the measurements, the observed data, averaged out roughly, to give you some idea that this is, and again, this seemed to be not something which had been really appreciated before, that it was all the information was in there, and it was pretty good. There is on the basis of our model, the theoretical value. There is the an average observed value. I'm leaving out the middle one for a moment, and this one is pretty good. This one looked rather unfortunate. However, it turned out, we found this out later, that this was actually the speed of much longer waves, so it really shouldn't be included in here. So we're beginning to ease towards a reasonable way of predicting what the speeds are going to be. That's the intermediate wave. One other thing that follows immediately is the ratio of the amplitudes. That's the surface wave and the thermocline wave. And that turns out to be, the surface wave over the thermocline wave turns out to be, at leading order in this asymptotic procedure, just minus r. And r, if you remember, was just a little bit small. So it means that if you have an enormous, and some of you may be very familiar with this, have an enormous thermocline wave below the surface, you won't see it on the surface. You won't see it there at all, or hardly at all. And also, you notice the minus sign means that it's out of phase. Okay, so that's the first little bit of information you can get. Of course, you can see you can just keep on almost forever. The other limiting set of results, which is fairly useful, would be very long waves. So now, not only is k going to 0, but we take kd going to 0 in the dispersion relation. So these are now waves that are long relative to the depth. They really are long. Okay, so this time we get the number of solutions that are real do vary somewhat as you change the parameters. Here we've got 1, 2, 3, 4, 5. These two are redundant so far as we're concerned here. These are the very, very fast waves. 200 meters per second, that's the typical speed for a tsunami. We're not generating tsunamis. I don't think we're generating tsunamis. Otherwise, I just do the same sort of thing that I did before. So what I've got here is a pair of values, a typical estimate, putting in our parameters from the calculation and the measured ones. So I've got a feeling, can I go back for a second? I think I wrote something, but I didn't comment on it. It probably means that you've... I thought it was there, yes, sorry. That's right, that second one, which is for very long waves, sorry, my mistake. The third one, that's this one here, turns out to be, and is observed to be, and there is data associated with it, we get eddies below the surface, turns out to be a critical speed. Okay, sorry I forgot to pick that up. Okay, so here we are, we've got the same sort of estimates that I gave you before. So we've got for very long waves, pretty good, or pretty good, and pretty good. They seem to relate fairly closely to what is observed. The ratio of amplitudes takes a rather different form. So this is, to get it right, for the first three. 1, 2, 3. So this one relates to that one, that's pair, and that one relates to this one. This is redundant, as I've already said. You'll notice that this one has the R in, but this one does not. But that V there was about 0.014, I think, and the D is 33. So it is still very, very small. The same effect, but produced in a quite different way. This one depends upon the velocity profile. This one, which was a real surprise, this one does depend, with a small adjustment, on what you'd expect, namely the density ratio. Okay, so pause there for a moment, have a little drink. So all of that is background, and was the starting point for rather more extensive discussions. As I said a few minutes ago, producing this result, which I would have thought was routine and should have been done, hadn't been done, and the feedback we got was rather positive. In a sense, that's why we did it, because we wanted to know whether we were doing something useful to the oceanographers, and it turned out it was very useful, and certainly we've had quite a lot of response from those who've done calculations for lots of varying wave numbers and putting in different models, and they seem to be fairly happy with the result. But it's not really the sort of applied mathematics I want to do. I want to do parameter asymptotics and then nonlinearity or something like that. So I'm going to just briefly outline what can happen. Well, you certainly can get critical levels appearing. You remember the profile looks something like this. So you can get critical levels. Indeed, you can get a critical level there, and here you'll get a pair of them, one high up and one low down. And that critical levels occur has been observed, because there have been observed associated with those 0.55, whatever it was, meters per second, associated at that level where that would be the appropriate speed of the wave associated with the speed of the flow, closed eddies have been seen. Right, and naturally going to be, so the thermocline is sitting here, so you've got them in the neighbourhood of where the thermocline is sitting. Right, so I'm going to use our equations, albeit a little bit of outline here, to obtain the structure of the flow for these critical regions. And you know the approach, because it's the one I gave you a little bit earlier this week. I'll just limit myself to the region 1, the one at the top there. And for it to be critical, the speed of the wave has got to sit between the minus v and the plus w. Okay, so all the story here, the basic structure, is the familiar one. You've seen this before. Introduce a characteristic variable associated with the speed c, and assume that we are able to follow that wave and there aren't any other wave interactions, albeit linear, coming from the other waves which are present. We'll assume that we've got some sort of compact support initial data, follow these various waves are produced, and we follow one of them, the one that we're interested in. The equations then take a form that you're, in general terms, familiar with, but of course I've got to write it in this notation, and in particular you see the description here, which is associated with the particular background flow in the neighbourhood of the region where we are saying we're going to have a critical layer. We're seeking for a critical layer structure. So everything is familiar there. We can find the solution outside the critical layer with a suitable wave number. This is exactly what we did before. So this is the simple linearized structure that you would get following Stokes, for example. So all of that follows directly from the sort of material that you've seen before, and what is more important is that you know what the scalings are going to be. There's nothing different here in terms of scalings. It's exactly what you have seen before. So if you have a wave of order epsilon on the surface, the neighborhood of the critical layer has got to be of size root epsilon. And you will remember that we have to be consistent with the equations, we have to do this, which doesn't look good, but remember, it's really epsilon u that we're dealing with. So this, in terms of the original u scaled, is root epsilon. All of that is then consistent with the equations. It's exactly what you've seen before, so everything is going to go through. Okay, so for the record, I've just written down the new system in the scaled variables, and therefore the system valid within the critical layer. Exactly as we did before, introduce a stream function, and the leading order solution, which is all we need, satisfies it's a vorticity type equation where this is an arbitrary function. We need to choose the f in order to satisfy the matching principle, as you've seen, so that you satisfy the conditions above and below. To match to the solutions which are outside the critical layer, which are the ones I showed you a few moments ago, then psi hat has got to take that particular form, and then we can determine the leading order as epsilon tends to 0 for the structure of the streamlines within the critical layer, and this is essentially the form of Kelvin's cat's eyes. This, of course, is purely periodic, and we know that the waves, the eddies in the Pacific, you're only going to get a relatively small number of them, maybe half a dozen or a dozen. They're very long. They tend to be very long, very big things, and there aren't that many in the region where the critical layer appears. I think that's right. Yep. Okay. Good. I had started to investigate how one might then take, because it's my main interest, take this scenario and then examine the way in which nonlinear waves start to evolve. This is much, much more complicated than it is for classical water wave theory. It can be done, but I haven't done it absolutely to completion. I have to admit that I just lost interest. I could see how to do it. I've even got all the scales, so I know it can be done in a general sense. And I really wanted to confirm that there did exist scales that would give us a balance between unsteady, nonlinear, and dispersion. But the background scenario here is such that it becomes quite a lengthy task. Right, so I'm going to make one or two concluding comments and then I will have finished. So what I've tried to show you, and these comments really apply to the week, what I've tried to show you is that the methods of parameter expansions can be used, I would like to think with some success, to extract fine detail of really quite complicated flows. Flows for which we do not have exact solutions. If we're very lucky, or we may have numerical solutions, we have some good, strong theorems in the background, so we have a rigorous development that tells us there are solutions of this type, they do exist, and then we try and extract some fine detail. That's the best of all possible worlds, of course, if we've got that in the background. Right, I've, in this particular case, because it expands the application, we're able to get a leading order problem which involves a general wave number, which seems to be, well, I've used the word gratifyingly good with the data that's available. And in principle, I can't say it any more strongly than that, in principle, this asymptotic approach, even in these complicated problems, allows an extension that will enable us to look at the way in which nonlinear waves evolve. Higher order terms, of course, for all of these problems, not just this one but the previous ones, are accessible, and they can be examined just to check whether we have any non-uniformities at certain times or in certain regions. Right, I'm going to make one or two comments to really finish off, and that'll be it. I hope that, I know my style is very different from much that you have seen. I hope that my approach to thinking about and setting up the water wave problem and saying a little bit about what solitary waves and Gerstner waves was worth doing, but above all, what I hope is that showing you via some examples and giving you the appropriate language that parameter expansions are a very useful tool to have in the armory of a mathematician who's going to be dealing with physically based problems. It is an addition, it's an extra to all the other techniques, the formal, the rigorous techniques that you're familiar with. And as you've seen from my presentation, it is not the road that I go down. There is enough for me to do to keep me busy for quite a lot longer. I think that's probably it. So, ladies and gentlemen, the entertainment is concluded.